we saw a lot of complexity measures, and we also saw that all of them were polynomially related. This is the figure which you have seen. Here, arrow represents that, like, let's say there is an arrow between df and degree of f. This shows that df is an upper bound on degree of f. Similarly, a lot of these relations were known, and then we were able to show that the bottom measures, again I am excluding sensitivity, removing sensitivity, whatever are the bottom measures, here in this case this is Bloch sensitivity in approximate degree, some power of them, some natural power of them bounds df. This is what we saw last time. We saw that df was bounded by BSF. This was the first result, which was which used the fact that df is bounded by certificate complexity times Bloch sensitivity, and then even certificate complexity was bounded by Bloch sensitivity square. This gave us the one side of the polynomial relations, and then we also saw that Bloch sensitivity was bounded by approximate degree square. Using this, everything was polynomial related. Can you tell me what did we use here? What was the idea of the proof here?
Okay.
Sorry? Sorry, I couldn't hear the answer.
We just saw the function on like weight 1 and weight 0 inputs. And then
no. So that was true for OR function, but in that case, wherever the sensitivity or Bloch sensitivity is achieved, right, there must be some input x where the Bloch sensitivity is achieved. We will move x to the Hamming weight 0.
Oh yes.
Right, and so given some function's Bloch sensitivity, we will create another g, which will look like promise OR, and which will just be a translation of f, in the sense that x will become 0, and whatever are the blocks, disjoint blocks, where which are sensitive, each of those blocks will give rise to one variable in the new function. And this translation does not affect approximate degree, but for the new function, approximate degree has to be lower bounded by square root of the number of variables. This is because of the Nissan and Szigeti result, which we saw long back, which also showed that the approximate degree of OR function is square root. So using the same technique, we can convert this into a promise OR problem. That was that. Whether in the promise OR problem, the number of variables will be equal to the number of sensitive blocks. I did not go into the details of this, but if you are confused about this, I strongly suggest that you look at the original. Okay, but this is a nice proof. This changes this approximate degree promise OR thing to a much general result, and then everything was polynomially related. Once we related everything except sensitivity to each other, the natural question is, what about sensitivity? Many people thought that it was not possible. Many people thought that there are cases when sensitivity is exponentially smaller than the other functions. Many people thought, no, it could be polynomially related. What is the truth? And that's what we have to figure out. Remember, f here is a what kind of function?
Total.
Yes, f is a total Boolean function. In this setting, we want to relate SF with degree. And to do this, the result was obtained. Actually, it was shown that everything actually is polynomial related, including sensitivity. And to do that, this was proved by Huang. And for that, Huang introduced another measure. Actually, in his paper, he does not name it as another measure, but now further work has shown that the quantity which he studied is in itself an interesting quantity. That quantity is called spectral sensitivity. I am going to define it in a moment, but let's see what Huang accomplished by introducing this. This is called spectral sensitivity, denoted as lambda of f. He introduced lambda of f, and by definition, it was quite clear that lambda f was a lower bound on sensitivity. Once you have that, forget about this dashed line. But by definition, you would know that lambda f is less than S. Now, even if you relate lambda f with any of the complexity measures polynomially, you are done. That means what you wanted to show was pick up a measure here and show that it is polynomially related, bounded by lambda. What Huang showed was if you choose A to be degree of f and C to be equal to 2, then this is true. And once you relate sensitivity or actually lambda with any of the complexity measures, you are done. So Huang's result was degree of f is less than lambda f. This is the theorem which Huang proved and solved sensitivity conjecture, got his paper into Annals of Mathematics, was a huge deal. So this is the theorem which you want to prove, but before we prove that, is it clear to everyone that why is this theorem sufficient to show the entire sensitivity conjecture? Are there any questions? So is it sufficient to show this degree f less than lambda f square to show that everything is polynomial? Is that clear to each of you? Raise your hand if it is not clear. Okay, good. So now you are very clear about polynomial relationships and you kind of see that they compose. So even if I relate anything with lambda, I am done. And Huang did it for degree. There were some further developments after this. The sensitivity conjecture was already solved, but the picture became actually much nicer when few people, Aronson, Ben David, Kothari, Rao, and Tal, they in 21. So last year the paper came on archive. This year it got published. So very recently they actually showed that lambda is a lower bound on approximate degree. So in some sense we have df at the top of the tree. Similarly, we have lambda f, which is actually a lower bound on everything. That is pretty cool, right? So it turns out that there is a central measure which relates the two sides. So if you had seen these complexity measures, certificate, block sensitivity, they were very, how I should say, randomized measures, combinatorial measures of complexity. On the other hand, degree and approximate degree were kind of algebraic measures. The only thing we knew was that block sensitivity was less than approximate degree. So is it possible that the algebraic measure is very, very large, but the combinatorial measures are very, very small? It turns out that cannot be the case. And Huang related them by introducing, in some sense, a common denominator to both sides of this. So lambda f is something which is a lower bound on sensitivity. It is a lower bound on approximate. Though remember that this lambda f less than approximate degree is not needed to settle sensitivity conjecture. Just by the fact that lambda is a lower bound sensitivity and lambda f square is more than degree is good enough. So this and this arrow were good enough to prove sensitivity conjecture. The blue dotted arrow is the new information which I'm telling you, but not required to show sensitivity. Right? So this was proven only this year or last year, you can say, that lambda f is a lower bound on approximate. The total picture in some sense looks like the thing on this. df is the highest thing, it's a common upper bound. Lambda f is a lower bound on f. Again, remember here that lambda f is O of approximate degree, not really less than approximate degree, right? So it's not as tight as less than equal to, it's less than some constant times approximate. That's what we are able to. I am not going to cover this blue arrow. The reference is given in the text and lecture notes. Feel free to read about it. We can discuss it later if anyone wants. What we want to see is this red dashed arrow. Degree of f less than lambda f whole square. This is what we are interested in. The first order, obviously, if you look at the figure, you know every other measure. The first thing, if I want to prove degree of f less than lambda f square, is to understand what lambda f is. I have told you, oh, by introducing lambda f, we accomplished a lot of things. But what is lambda f? What is its definition? For introducing lambda f, I have to talk about the sensitivity graph of a function. Do you remember Boolean hypercube? What is a Boolean hypercube? Let's say Boolean hypercube on n vertices.
A graph whose vertices are all the possible inputs from 0, 1 to the power n.
Correct.
And an edge exists between two inputs whose having distance is exactly 1.
Thank you. Thank you. Very good. Right. So what is a Boolean hypercube? The vertices are the 2 to the power n vertices, 0, 1 to the power n, all the inputs of a Boolean function. And edge xy is an edge if and only if the Hamming distance between them is 1. This is just to remind you. This was a Boolean hypercube as a graph. And now the sensitivity graph is going to be a subgraph of it. You are going to pick some edges out of Boolean hypercube. So keep all your vertices. Again, remember, sensitivity graph depends on the function. A graph, a function leads to a sensitivity graph. So given a function f, the sensitivity graph is a graph with the same number of vertices as Boolean hypercube, v is equal to 0, 1 to the power n. And it will have only edges from the Boolean hypercube, but only those edges where the vertices have different functions. So x and y will have an edge if fx is not equal to fy and xy was already an edge in Boolean hypercube. That means the Hamming distance between x and y is 1. So what are the maximum possible number of edges in a sensitivity graph?
S of f. From a
No,
vertex,
no.
there can be at max S of f.
Very good. Very good. That is correct. So the degree of the sensitivity graph is the sensitivity of the function. Very good, right? So now this is not the algebraic degree, but the graph degree. People are familiar with graphs, right? They know what graphs are. Okay, I assume everyone is. So the degree of the graph is sensitivity of the function. But I am asking, what are the number of edges in a Boolean hypercube? How many edges are there in the Boolean hypercube? In a Boolean hypercube, what
n
is
times 2 power n minus 1.
sorry, n by
N times 2 power n minus 1.
n times 2 to the power n minus 1. Very good, right? That is because every vertex has n edges, and then you divide by 2 because every edge takes part for 2 vertices. So n times to the power n. So these are the maximum number of edges in a sensitivity graph itself, right? So is the definition of GF clear? Are there any questions about GF? Okay, if there are no questions, then it is my turn to ask a lot of questions about sensitivity graph. First is a what we call full toss in cricket, right? The easy one. Is sensitivity graph a subgraph of Boolean hypercube?
Yes.
That's how
Yes.
it was defined. So yeah.
Right, so that was very easy, right? That's why I called it's a full toss. You were supposed to hit a 6 on that, right? So that is easy. Let's take it to a step further. Let me ask a question which is slightly more difficult. What is a function whose sensitivity graph has maximum number of edges? So the maximum possible number of edges are n to the power n times to the power n minus 1. Is there a function whose sensitivity graph has all the edges of Boolean hypercube?
Parity.
Parity and its in complement.
Right, very good. But there are two functions, parity and not of parity. And as an exercise, not now, you can probably take it home, but you can try to show that these are the only two functions whose sensitivity graph has all the edges from the Boolean. That is not hard. Okay. How many edges are there in sensitivity graph of or to the or n?
N.
Sorry?
N.
N. Very good, right? The only edges are present in the first layer, right? The between Hamming weight 0 and Hamming weight 1. After that, function value is not different. So, you know, when for or, this is the Boolean hypercube, only these edges are present and all of the edges at the bottom are present. Rest all will not be part of the sensitivity. So that is great. Question 1 was, is sensitivity graph a subgraph of Boolean hypercube? That was clearly correct. Now let me ask the opposite question. Is every subgraph a sensitivity graph for some function? You can give me a proof of this, or you can give me a subgraph which will not correspond to any sensitivity graph or sensitivity graph of any function. I don't know which one is true. You have to tell me. Is the question clear? Raise your hand if the question is not clear. Okay.
A cycle.
What do you mean by cycle? What are the vertices? You have to tell me in 0, 1, comma.
So from each level, you are picking one. I mean, from the first and the last, you are picking the one vertices. While from every other layer, you are picking two vertices.
From the first, so Hamming weight 0 and Hamming weight n.
Yes.
Okay.
And from every other layer, you are picking two vertices.
So you are saying all these are edges. Is that correct?
No. Like from the Hamming weight 1, you are picking only two vertices.
Okay.
Similarly, for Hamming weight 2, Hamming weight 3, and then you construct a cycle.
So I don't understand what you mean by cycle because there are no directions.
So, okay. I mean, if you are connecting this this one particular vertex to only one of the other vertices. Like for Hamming weight 1, you making it adjacent to only one vertex in Hamming weight.
Like you mean, okay. So these two are edges and then this is edge. Is that what you're saying?
Yes.
Okay.
Yeah, and then we keep on doing this till we get to the final Hamming weight at the level corresponding.
The final layer.
Yeah.
Okay. And why is this not possible? Why is this cannot be a sensitivity graph of function?
Because say supposing you are taking Hamming weight or two, Hamming weight 1 and Hamming weight 2 level corresponding to that. Since we don't have an edge between one of the vertices, so we are saying that I mean, so this means that the value was same over there. The value of f was same.
At this level, right?
Yeah.
At Hamming weight level 1, the value is same. Yes, for both the vertices. That is correct. Because whatever was fx here, this will be not of f of x, right? At both the things.
So the thing is that I think it is actually true that every sensitivity graph, because if you consider the whole Boolean hypercube, then it is I think it is a bipartite graph because you can split it into those inputs, even Hamlet and those odd Hamlets. Obviously, an edge will be only between these two set of vertices.
Okay.
And so because it is it cannot have cycles of odd.
Okay.
And so if we
if
we have a sensitivity graph, we can.
So there is an easy way to check it, right? Every graph, every function will have a different sensitivity graph. You agree with that? Like by a factor of 2 at most, right?
Yeah.
Right. So how many functions are there?
2
to the power
2 power n.
To the power 2 to the power n, right? And then the number of sensitivity graphs will be divided by 2. Corresponding to them, right? Because two functions will have the same sensitivity graph. And how many sensitivity graphs are there? How many edges are there?
Like 2 to the power n times 2 to the power n minus 1.
So how many, how should I say it? How many subgraphs are there?
2 to the power this number.
Correct, which is much bigger than this. So clearly there are subgraphs which are not sensitivity graph for any function. This is just by counting. Now you are trying to, you have to create a function. So one thing which was just mentioned, that doesn't seem to be correct to me.
Like what we start with, like with all zeros and give it some value, and then whenever we find an edge, we like give the complement value and go all the way up to all ones. So like why would it be a problem?
Yeah, so what I'm saying is the graph which was mentioned just now, which is on the left of the screen, that could be a sensitivity graph of subfunction, right? Why can't it be a sensitivity graph of any function? That
yes, like any symmetric function would do, which alternates upon these Hamming weights.
No. But for symmetric function, there will be more edges, right? I think the point is that these are the only edges. For a symmetric graph, in the first layer, either everything is an edge or nothing is an edge. Right? So whoever, I forgot who told me this graph, right, on the left top. Why is, do you have an argument that why can't this be a sensitivity graph?
I know my argument was based on this, that for simplicity, say supposing we have A and B, on A, the vertices on the first level are A and B, and on the second level are C and D.
Okay.
So Now, as A and D are not adjacent, this means that
What
they
do you mean
have
by A
different
and B are
values.
not A and B are not exclusive,
No, A and D are not adjacent.
right? But A and B do not have an edge in the Boolean hypercube, right?
No,
Their Hamming
D,
distance is
D.
A and D.
Yeah, yeah.
A and D are not adjacent, but they might not be part of the Boolean hypercube.
No, we are taking consecutive levels. Right?
So then you have to tell me what exactly C and D are. Everything on Hamming weight 2 is not related to everything on Hamming weight 1, right?
Yeah, yeah.
But okay, so yeah, so you might have a good idea. Let me just say you can actually create a very simple graph, right? So think of 0 0, 0 1 1 0 and 1 1, right? Suppose I tell you that this is an edge and this is an edge, right? That means if the function value was 0 here, it
Okay.
must be 1 here and it must be 0 here. Now, if I create an edge here, what does it mean? What is the function value at 1 0?
1.
1. So that means this edge has to be there. The edge between 0 0 and 1 0, it has to be there. So just now the subgraph which I have made cannot be a sensitivity graph of any function. Just the subgraph which has just these three edges. Is that okay? Because if these three edges are there, the fourth edge has to be there. That is what you have shown. So a subgraph which has only these three edges does not belong to any sensitivity graph. Is that okay? Is that should I make it on a next page and make it more clear? Is it clear?
It is clear.
It's clear. Okay, good. Right. So okay, so this was just to make sure that you are now familiar with sensitivity graph, right? Good. Once we have defined sensitivity graph, then I can talk about spectral sensitivity. I can define the spectral sensitivity of the function. For any function, any Boolean function, how do I define the spectral sensitivity? I just create the sensitivity graph and find the biggest eigenvalue of the sensitivity graph. When I talk about eigenvalue of a graph, I mean eigenvalue of its adjacency matrix. So I've underlined a few things just for a sanity check. Is there anyone who doesn't know the meaning of eigenvalue? Okay, good. What about adjacency matrix? Everyone knows what is an adjacency matrix of a graph? You have vertices lined. And then when do you have 1? It's a 0 1 adjacency matrix, is a 0 1 matrix, and you have 1 if
There's an edge between the two nodes.
right, Vi and Vj is an edge. Okay. So can I assume that each of you know what adjacency matrix is? Right. So if you now you know what adjacency matrix is. So when I say eigenvalue of a graph, I mean eigenvalues of the adjacency matrix of the graph. So, and now we can talk about eigenvalues of a function. What do I mean by eigenvalue of a function? Eigenvalue of a function is eigenvalue of its sensitivity graph. What is eigenvalue of its sensitivity graph? It's the eigenvalue of the adjacency matrix of the sensitivity. So now, given a function f, what are the dimensions of its sensitivity graph? Sorry, what are the dimensions of the adjacency matrix of the sensitivity graph? What are the number of columns and what are the number of rows?
2 to the power n times 2 to the power n.
Very good. How many eigenvalues are is it going to have? It's
2 to
slightly
the
different.
power n.
Why?
Because the characteristic polynomial has the degree 2 to the power n.
Why does it have degree 2 to the power n?
Due to the characteristic polynomial for the adjacency matrix.
So are you saying that for any matrix of dimension 2 to the power n cross 2 to the power n, the number of eigenvalues are 2 to the power n?
If we are not, if we are also including the order of those eigenvalues, like
Multiplicity, I think you want.
Yeah, including multiplicity.
yeah, multiplicity.
But every 2 to the power n cross 2 to the power n matrix has all the 2 to the power n eigenvalues. Everything is completely diagonalizable,
No,
right? So what is special about AF?
it's
Yes, it is symmetric. If there is an edge between Vi and Vj, then there is an edge between
Vj and Vi also.
Vj and Vi, right? So all its eigenvalues are going to be real.
Hmm.
So AF is going to have 2 to the power n real eigenvalues. Okay, and once we have real eigenvalues, we can talk about which one is bigger, which one is small. So then the spectral norm of A of F, or the biggest eigenvalue, is the spectral sensitivity of the function. Okay, what do I mean by biggest eigenvalue?
The largest.
Right. There might be a confusion here, right?
Largest in magnitude
Very good.
or
Yes.
just the
Yeah.
largest?
So suppose I had 3 eigenvalues, or let's say 4 eigenvalues like this. Then what is the spectral norm? Is it 4 or is it 1? What is the biggest eigenvalue? Is it 1 or is it -4? So it turns out when we talk about spectral norm, we talk about the eigenvalue which has the biggest magnitude. So if the eigenvalues are like this for a matrix, then its spectral norm would be 4. That means the highest stretch possible for a vector, right? If I take a unit vector v, how long its length can become? And in this case, its length can become 4 times the original length, right? That is called the spectral norm, and that is what I mean by biggest eigenvalue. But luckily, in this case, this confusion will not arise. That's the good thing. And the reason is for this adjacency matrix, for this particular adjacency matrix, when I talk about the sensitivity graph, the adjacency matrix of it is going to be special. The eigenvalues of it are going to be symmetric around 0. That means if lambda is an eigenvalue, then minus lambda is also going to be an eigenvalue. Let's see why that is the case. First claim is Boolean hypercube is bipartite. Do you agree? If you agree, then you have to give me a partition with which Boolean hypercube is bipartite.
I agree. And
Sorry, your voice is breaking.
hello.
Yeah.
Hello. Yeah. So
Yeah.
the Boolean hypercube is bipartite. So the partition is one of the set is the set with even having weight, set of inputs with even having weight, and the other is the set of inputs with odd having weight.
Perfect. Perfect. So if I define two sets, A is the Hamming weight X such that X is even and B x such that x is odd, then it is clear that my graph Boolean hypercube is bipartite. That means there are no edges inside A and there are no edges inside. And since Boolean hypercube is bipartite, any subgraph will also be bipartite. And actually, in this case, the size of the bipartitions, the size of A and size of B are actually equal. So this is a fact about any sensitivity graph. The sensitivity graph is very, very special. It's actually a bipartite graph. And for a bipartite graph, it turns out that your eigenvalues are symmetric. But is it clear that Boolean hypercube is bipartite? Any questions about that? This should be clear to you. You look at the Boolean hypercube, there are no edges between the first layer and the third layer, or first layer and the fifth layer, so on and so forth. The only edges present with the first layer are with the second and with the zero element. So if you look at an edge, one of them has to have Hamming weight even, one of them has to have Hamming weight odd. This is not surprising, right? Now, if the subgraph is bipartite, then look at my adjacency matrix, right? I will write it in a special way. I will first write A here and then B. So what do I know about the first quadrant, top left quadrant of this matrix? What about the edges between A and A? What should I get here?
All 0.
Correct, because there are no edges inside A. Similarly, the diagonal down entry between B and B is
Null matrix.
all 0, right? Because there is nothing. And then if my graph, if my matrix is G here, what is the matrix in the remaining quadrant?
G transpose.
Why?
Because I mean, if U is adjacent to B, then
It is symmetric, right? AF is symmetric. So my matrix looks like this. And now what you can check is that suppose lambda is an eigenvalue, right? My claim is that minus lambda is also an eigenvalue. What will be the eigenvector for that? So V in itself is a vector of the required dimension. Similarly, U. Now, if this is true, I want to create a vector whose eigenvalue is minus lambda. What is that eigenvector?
Minus V minus U.
That is not correct. Why is that not correct? What is the eigenvalue corresponding to minus V and minus U?
Okay, that is lambda itself.
Okay, probably I've put you on spot, but you can easily check that this is true. So if you just negate the entries in U, you will get an eigenvector with eigenvalue minus lambda. This is something which you can easily check. I can't give a better proof than this. You have to just convince yourself. You can just see how G, V, U are related, and then the second thing. Right. So what this is showing you is that your eigenvalues are symmetric around 0 for a sensitivity graph. So AF, this is the adjacency matrix of the sensitivity graph. Its eigenvalues will look like something 0, and then all the values before 0 will be repeated after 0, just with the sign switched. Okay, so then there is no confusion about biggest. Now, noticing all this, is the definition of lambda clear? Because this is the most important thing, right? We are going to say that degree is bounded by lambda f square. We should understand the definition of it. So are there any questions about the definition of it? Okay. Raise your hands if I can go forward. Okay, Anindya, do you have any questions? Okay, good. So the lambda is clear to all of you, the definition of lambda. Now, all the other measures we noticed were kind of between 0 and n. So we just first want to check, is it even true for lambda? Is it between 0 and n? Clearly, lambda f is greater than 0, greater than equal to 0, right? This is not a question. Eigenvalues are symmetric around 0. So the minimum eigenvalue will, the maximum eigenvalue will at least be 0. Why is lambda f less than equal to n? Let me just tell you this. These are the things which you notice when you play with eigenvalues. But if you look at any row, what is the maximum possible sum of any row in AF? Remember, AF is the adjacency matrix of the sensitivity graph.
And
It is n, right? Clearly, in Boolean hypercube, everything is related to at most n things, right? So then the degree is bounded by n. And now my claim is that the maximum eigenvalue of a matrix is less than the max. This is less than equal to. And this is a simple proof that the maximum eigenvalue or any eigenvalue of a matrix, its value is less than maximum row sum. Okay, that is something which you can easily figure out. Just look at the eigenvector, see where is your maximum entry. Okay, and you will see that that maximum entry can't go more than max row sum times the maximum. Okay, so I'm not going to give a complete proof of this. I'll leave it to you as an exercise. But the statement, is the statement clear? For any matrix, any eigenvalue is actually between its maximum row sum and minimum row sum. And sorry, the maximum eigenvalue, I meant. The spectral lom of A is between minimum row sum and maximum row sum. Okay, but you can prove it. Okay, so now what is the spectral sensitivity of parity? What is the lambda of parity? Lambda.
All ones except the diagonal.
No. You are telling me the matrix. I'm talking what is the maximum eigenvalue of the sensitivity graph. So what is the sensitivity graph of parity?
Okay.
What is the sensitivity graph of parity?
Boolean hypercube.
Boolean hypercube. Now in the Boolean hypercube, every row sums up to n. So maximum eigenvalue is n, right? Because
How
minimum
can
row sum
you-
is
okay. Sorry.
right. So lambda of parity is just going to be n, and you can actually check it very easily. Just take all one matrix, all one vector, right? That will be an eigenvector with eigenvalue. Okay, that's a simple proof. all ones eigenvector. Actually, this is true for any regular graph. For any regular graph, its highest eigenvalue is the degree of the graph. What about lambda f less than equal to sensitivity of f?
Is a regular graph?
A regular graph is a graph whose where vertex, the degree of every vertex is the same.
Okay.
Right? So every row will have equal number of ones, and that is going to be the maximum eigenvalue by the same theorem, min row sum max row sum. You can just check this all ones vector will be the eigenvector. These are small facts which you can actually try for yourself. This will actually give you practice with calculating eigenvalues. What about lambda f less than equal to sensitivity? Why is that true?
Because the max row sum can be sensitivity in the
Very good, very good. So max sum is actually equal to sensitivity by definition, right? The row of x, that the sum at any row is actually the sensitivity of f at that input x, right? So max row sum is the sensitivity. And in some sense, that's why I'm calling it spectral sensitivity, because this is encoding sensitivity in some sense. Okay, good. Now, knowing all this, this is where we are, right? This we have proved this arrow. Sensitivity is less than lambda. Sensitivity is more than lambda. This is done. The only thing we don't need to prove now is this. Lambda f, relationship between lambda f and degree f, and then we will be done.
So lambda f is less than equal to max degree or equal to max degree?
Lambda f is not equal. See, this degree, when you say degree, you mean the degree of the graph or you mean the degree of the function?
Okay. Max degree, I mean of graph GF.
It is less than that. If it was equal, then lambda f will be equal to sensitivity.
Yes, okay.
Right? So in general, we know that lambda f is less than equal to sensitivity, but if every input had the same sensitivity, if for all x, s f of x had the same value, then lambda f is equal to sensitivity.
Okay, yeah.
Right? Because every row will sum up to the same. Okay, so we are now at this picture. We have proved this arrow. The other direction, degree approximate f, is more than lambda f. This is something which I will not prove. This is not even needed for the proof of sensitivity conjecture. But if you are interested, you can find the reference, the lecture. Okay, so then the only thing which we need to prove now is the main. This is the setting is done now. Well, now we want to prove Huang's result. And what is Huang's result? For any Boolean function f, this is true. Once we prove this, we have shown all the measures are polynomially related. This is our remaining task. For today and tomorrow, for actually this course, this is the final thing I'm going to prove, and then you'll be presenting projects next week. By the way, for the projects, look at your schedule on the website. I've already put when who will be presenting. If that is not good for you, talk to one of the persons with whom you want to switch. But you should be there for all the presentations. It's a class time. You have no excuse not to be there. So you should be there for everyone's presentation. Okay. Okay. Is it clear what we want to prove now? Any questions? Remember this degree, don't get confused with the graph's degree here. This is the degree of the polynomial, which represents f. This is the Fourier polynomial, right? Degree of the polynomial representing f. we should not get confused with the degree of the graph. There is no degree of the graph here. The degree of the graph was the sensitivity. We don't care. At this point, we are going to ignore it. The result is, if you take a function f, the Fourier degree of it is bounded by the maximum eigenvalue square. This is what. Any questions about our target? Okay, good. So we are fine with the target. Let's see how we can simplify our target a bit. We can make some assumptions, and then our life will be much simpler. My first claim is that I can actually assume degree of f to be equal to n. I will give you a minute and see if you can come up with an argument. It's not straightforward, but it's not very difficult. The point is, when I want to prove Huang's result, for us, Huang's result is this elongated circle, degree of f less than equal to lambda f square. This is the only thing which I want to prove now, right? I proved this. I'm done with sensitivity conjecture. So this is where you should focus, right? Just keep looking at it. This is what you want to focus. And if you are focusing on this, then the first claim is that we can assume degree to be complete. The question is why? Any ideas? Okay, first, let me ask you this. If this result is not true, if Huang's result is not true, that means there exists a function whose degree is more than lambda f square. Right, for the sake of contradiction. If using this, if I show that there exists a g such that degree of g is more than lambda g square and degree of g is complete, then I'm done. If I can prove this, then I can assume degree g to be complete. Is that okay? How we will create g, it's a separate question. But if I can create a g like this, that means it's enough to show this degree of f less than equal to lambda f square for a complete degree function. If I show this implication, that then I can only focus on complete degree functions. Is that okay?
Yes.
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 Right. Because if there is a function which is violating this equation, then there has to be a function which violates it and has full degree. But we have shown that for full degree there is no violation. Right. So now think about how to convert f into g.
By, let us say, I mean, I'm thinking this way. So if there is some highest degree term f, which in f polynomial representation, so we multiply the remaining variables like whole. Let us say x1 is not in the highest degree term, so we multiply x1 to the polynomial representation. Then it will have degree n, and I think then the adjacency matrix will have more ones. Like the number of ones won't reduce.
Okay. So look at the polynomial representation of f. Let's say the highest degree term is x1 to x. The degree was k, right? So g is equal to f times xk plus 1 to xn. Is that what you are saying, Udit? Is that correct?
So this is G and it will have degree n.
Correct. The degree, no, it will not have degree n, right? Wait. Yeah. Okay. It will have degree n. But
And
what will,
since if we have the previous sensitivity graph, so what will now happen is that these x1 to xn, these values would also like add new edges to it, right? So that's what I was thinking.
mm, that's not clear, no? You are saying that the lambda will only increase now. Is that what? Sorry, what are you saying?
I'm saying that the number of rows and number of ones in any row in the matrix would only increase.
Yeah. Why is that true? Why is that true? That's not clear. No.
Yes.
No. But you can simplify it more. Instead of multiplying it by xk plus 1 to xn, we have learned about restrictions, right? What if I restrict my function to something, xk plus 1 to xn, set them as you like, 1, -1, whatever. Okay. Then what will be the degree of G? I'm defining G to be f restricted to xk plus 1 equal to 1, xn, let's say 1. Let's keep them all as 1, but you can actually keep them as whatever you want.
The degree would remain the same.
Right? Because there will be no term which will match x1, x2, xk, right? That term will not be cancelled out. By putting the restriction, x1, x2, xk term will not merge with any other term, right? Because there is no higher degree term than x1, x2, xk. Right? So do you see that degree of G is equal to k is equal to number of variables in G? Do you agree? Questions about this? This restriction trick we have seen last week, or week before that, right? What do you mean by xk plus 1 equal to 1, xn equal to 1? We will just substitute these values in the Fourier expansion, and then what term can match up with x1, x2, xk? Any term which has to match up with x1, x2, xk, it should have more variables, right? It should have some variables from xk plus 1 to xn. But that means that monomial has a higher degree. That was not possible. I have picked the term with the highest degree. So that means in the Fourier representation of G, x1, x2, xk will survive with the same Fourier coefficient. So the degree of G is equal to degree of. What about approximate degree? Sorry, what about lambda?
Would be same. Like the number of nodes would be reduced for G this time, but the edges like would be the same.
Yeah, so what you can show is that lambda of G actually is going to be less than lambda of F. Okay, and this is true for any restriction. When you restrict your function, right, your number of edges, you are kind of getting a subgraph of the previous graph. So this is again as an exercise, you can see that. But when you restrict your function, your lambda decreases. So that means if degree of f was more than lambda f square, now lambda g is less than lambda f square, and degree g is equal to degree of f, then this condition has to be satisfied. degree of G is full. So we have created a function which has full degree and which still violates Wang's result. There is a small this lambda G less than lambda F, but you can do it. I'm giving you as an exercise. You should be able to figure this out. That the sensitivity graph, when you restrict the function, the lambda G just reduces. Okay, actually, whatever was the eigenvector which was achieving the maximum stretch, you can just restrict to the old values. It will still have the same stretch. In some sense, that is the proof. Okay, but yeah, again, you can figure this out. If not, we can always discuss it on the hello code. So that means I can assume my degree to have full degree, but that means I just need to prove this. For any function f with degree f is equal to n, lambda f is more than square root n, right? This is now our focus. By the way, on the right hand side, what I am drawing might not look like an eye, but I am trying to draw an eye, right? So we are focusing on this now. We know that degree of f is equal to n, then lambda f is more than root n. If we prove that, we can prove one. Now, again, this will take some time. We will complete the proof tomorrow. But what I want to understand is, what does it mean that degree of a function is equal to n? Specifically, define these two sets, V0 and V1. V0 is the set of all x's where function agrees with parity. V1 is the set of all x's where function does not agree with that. Okay. What about V0 intersection V1?
Null.
What about V0 union V1?
Entire space.
Entire Boolean hypercube, right? Now, good. So now you understand V0 V1. What does it mean that degree of f is equal to n in terms of V0 and V1?
Yes. Size of V0 is not equal to the size of
Very good, very good. Who was that? Aditya.
V1.
Was that Aditya?
Yes.
Yes,
Yeah,
very
it
good.
was me.
Yes, very good. Why? Because what is the nth degree Fourier coefficient? There is only one monomial of degree n, right? And what is its value?
Parity.
No. In terms of V0 and V1, it's the inner product with parity, which basically means
V0 size of V0 minus size of
V1. Exactly. Right. So degree of f is equal to n is same as saying that the Fourier coefficient of x1 to xn is non-zero. Right? And Fourier coefficient of x1 to xn is just this quantity, 1 by 2 to the power n, V0 minus V1. So what we are saying is that if the size of these two sets are not equal, then lambda f is greater than equal to root. Okay. This is now our target. But let me just more simplify it. So without loss of generality, I can assume that V0 is greater than V1. Why?
Otherwise, I can have the complement function.
Exactly. I can look at 1 minus f, lambda will not change, degree will not change, and still the same conjecture will be false. So again, I can assume V0 to be greater than V1. That says that if V0 is greater than what? If V0 is strictly greater than V1, then the size of V0 is bigger than what?
2 to the power n minus 1.
Plus 1. Oh, sorry. Yeah. Strictly greater than to the power n minus right? So this is what we want to prove. We have again simplified it much more. But okay, this is fine. This is degree of f. The relation of degree of f with V naught is obvious. But what is the relationship between V naught and lambda? Why is V naught or V1 important for lambda? Or let me give you a hint. Why is it important for sensitivity graph?
Because sensitivity graph of parity is the entire space.
Okay. No. Actually, sensitivity
Since the
graph is
sensitivity graph of parity is entire Boolean hypercube, so, and like this could in some way determine the number of edges like, give upon.
no. Actually, the relation is very clear. Not clear, I would say, not easy to figure out, but it's a very strong relationship.
So all inputs in V naught lie in the same connected component in the sensitivity graph.
Okay, it is more very strong than that, much stronger than that.
May it related to the main graph G, V0, V1.
Sorry, what is?
It is related to the main graph G in sense of some eigenvalues or
No. So actually, let me tell you this. Let me finish with this statement, and then you can think about it. We will finish the proof tomorrow. Actually, you know what is the sensitivity graph? You have the Boolean hypercube. Okay. You pick V naught.
V naught will be a subgraph of that sensitivity graph.
No,
V naught will
actually,
be a whole hypercube
yes,
on less
you take
inputs.
all the edges of Boolean hypercube inside V naught. You take all the edges of Boolean hypercube inside V1. There are no edges between V naught and V1. This is your sensitivity graph. Your sensitivity graph is actually union of two graphs. Subgraph induced on V naught. V naught union subgraph induced on V.
How do we create the edges in V0 and V1?
Whatever inside V naught, pick two vertices. If there was an edge inside Boolean hypercube, then you keep it. If it was not inside Boolean hypercube, you don't. That's all. That is what
Okay.
it means by induced, right? Inside V naught, induced means if something was an edge in the Boolean hypercube, I will keep it. If there was no edge inside the Boolean hypercube, I will not have it. So the only edges which are removed in the sensitivity graph are the edges which were there between V naught and V. So you draw V naught and V1, you remove all the edges between V naught and V1 in the Boolean hypercube, you will be left with sensitivity graph. And the proof of this is not difficult. Once I tell you this, you should be able to. And then if this is the case, what are the eigenvalues of GF?
so V0's eigenvalue plus V1 eigenvalues.
Yes, eigenvalues of V0 plus eigenvalues of subgraph induced on V0 union eigenvalues of subgraph induced on V1. So actually the Huang's proof is basically this. It has nothing to actually to do in some sense with a function. It's a statement. It's a combinatorial statement about Boolean hypercube. Pick any induced subgraph of Hn such that number of vertices are greater than half the size. You pick any set of vertices in a Boolean hypercube whose size is more than 2 to the power n minus 1. You take the induced subgraph. Remember what it means by induced. Induced means you do not miss out on any edges between the vertices of the student set. Of Hn on some vertex V, the size of V is more than 2 to the power n minus 1. Then the induced subgraph, I am calling it GV, the spectral norm of it is more than. This is Huang's proof. Notice this statement has nothing to do with a function. It is just giving you property of Boolean hypercube. That is the beauty of this proof. We have forgotten about the function now. It just says, take the Boolean hypercube, pick up any big set of vertices. Big set of vertices means it has more than half the vertices. Then there is at least one eigenvalue which is more than. Are there any questions? One thing I would want you to check by tomorrow is to see this this fact that the sensitivity graph is just the induced subgraph on V0 and the induced subgraph on V. Please try this. This will really help you a lot to understand this. Okay. And once you notice this, then this is what I need to prove. I was given degree of f is equal to n, which meant that at least one of the subgraphs will have size more than 2 to the power n minus 1. And for that induced subgraph, I will prove that the eigenvalue is more than root n. This is the target for tomorrow. This finishes the lecture for today.